Good morning and welcome to another webinar in the Industrial Heating Equipment Association series on sustainability and decarbonization. My name is Helen Tuttle. I am on the IHEA Board of Directors, and on behalf of the association, thank you all for joining us. We are excited to continue this series on such an important topic for everyone in the industry. Don't forget to check out the additional webinars we have added to the calendar on the IHEA website. Before we get started, I would like to remind everyone that all attendees are on mute. If you have any questions along the way, please type them in the questions panel. The speaker will address questions at the end of the webinar. All attendees will receive a brief survey after the webinar. It will take just a few moments to reply. We appreciate your feedback as IHEA continues this critical initiative for the industrial heating processing industry. One last announcement. This webinar is being recorded and will be available in the sustainability area of the IHEA website within the next few days. You will receive an email once the link is available. Now, I would like to introduce the presenter for today's webinar titled The European Approach. Dr. Joachim Wunning founded WS Inc. in 1997. He received his engineering PhD from the University of Aachen in Germany. Dr. Wunning has been the general manager of WS GmbH since 2001. He's actively involved in research and development efforts for the transition to renewable energy. Thank you for being here today, Dr. Wunning.
Thank you, Helen, for the introduction, and thank you, IHEA, for having me for that webinar with the title, The European Approach. Of course, I think there's not one and only European approach, but at least maybe I can get you some European specifics, which might be different than compared to the United States, and give you an opinion just from this side, what we do here with sustainability, and especially, of course, with the energy transition because of climate change, which is, I think, the main topic for the heating industry, burning a lot of fossil fuels. Yeah, why do we do all that? And I can maybe a little shortcuts and say, because the kids told us. I think you know, a couple years ago, 4 or 5 years ago, thousands and thousands of kids were out on the streets to remind us that we have to take better care of our Earth. And so they marched every Friday, sometimes with pretty funny signs. The one here will read, rescue the world. It's the only world with beer, so no beer on Mars so far. And like I said, but of course it's a quite serious topic also, and many people here in Europe took it serious, and basically no major political party now is opposing these goals to get away from fossil fuels and to get into renewables and to change our way how to treat the energy issues with here. So I think here in Europe we have a pretty broad agreement that we have to do some things. Of course, I think as in the United States, opinions on how fast it should go and who should do what are quite different, and it's quite difficult, of course, also to really, after having some announcement like the Paris Agreement to get rid of fossil fuels, then to really do it, to change your car from diesel or gasoline to electric, and it will only go a couple hundred miles. And all these are different things and difficult things, and especially for us in the heat treating industry, where we're using dominantly natural gas, it's a not so easy task. However, I think the energy transition, and that was also found in the demonstration by the kids, in first They mainly targeted to get out of coal, and we thought with natural gas, because it has much less carbon content than coal, we thought we have a bridge technology we can use quite a bit longer than coal, because natural gas is not so bad at all. We thought, okay, at least for the next couple decades, we could use that natural gas and be fine with it. However, of course, all of you are aware that something happened. It's probably now just over a year, September last year. Our big supply for Germany, Nord Stream 2, a natural gas pipeline bringing in natural gas from Russia, exploded. So before it was shut down anyway, but we thought temporarily. Now really it's pretty much destroyed, and it was kind of a additional wake-up call for us that we have to put more effort in to get out of the fossil fuels, because it's not only the climate change, at least in Europe, it's also the dependency on imports from not so good sources like Russia, what we have seen. I think in the United States, many people warned Europe, and especially Germany, not to build these pipelines because of our dependency. Now, of course, it's solved. A solution was found on its own because it's exploded. Now we don't have it anyway, and we have to see how to get natural gas from other sources like LNG. Some of the natural gas is coming out of the United States, but of course, importing it with ships is much more expensive rather than getting it through a big pipeline. So that puts also pressure not only of getting rid of coal and mineral oil, but also to get rid of the natural gas. And I think the car industry faced these challenges earlier. Everybody was aware that we want to get out of the oil and into electricity. That's a pretty clear path. However, hydrogen, there is also an option, but at the moment it's mainly electric cars. So what can we do to really target these things? We have some people here, I think it's the same as the United States, they just think, let's put up enough photovoltaic, solar power, solar modules and wind turbines in all areas. In some areas, maybe water power also, but not everybody lives in Iceland where you have enough water power or thermal power. In most countries, and especially in Germany, pretty much the only option for regenerative energy we have is solar and wind. And like I said, many people think, okay, let's build enough of them and we'll just have everything electrified, and that's very efficient and very clean, and then that's done. However, of course, it's not that easy. There's one problem with the regenerative solar and wind is that they are fluctuating. A power plant we can turn up and down depending on demand. We can get more or less power out of it. With solar and wind, we just have to take what we get from solar and wind. So at night, obviously, there's no solar power, and if there is no wind, we have no wind power either. So we have, certainly, if we build up capacity with wind and solar, we will have times where we have excess power, but we also have to have where we will have extended times where we have not enough power solely from wind and solar. We have a little biomass we can control up and down to a certain degree, but the biomass power generation is very limited. And as you can see here on these graphs showing the yellow solar in summer, the blues are wind power, and the green is biomass. Though there is still a wide gap in production and consumption. The consumption is a red line up there, which goes up and down by day and night, but there's still a pretty big gap. Not so much in summer if the sun is shining, but pretty much in winter when there's no wind, there's a huge gap we would have to fill. Now people think, okay, we have batteries. but if you think of these gaps are gigawatts, so these are enormous amounts, and you cannot have so many batteries for storage so much power that you could use your or have your furnaces heated by electricity at night. You know, it's a big amount of energy. I calculated it for an average annealing line, for example. I think for a couple days of low wind in winter would means you have the batteries of a couple 100,000 Tesla cars to have enough energy for your one single furnace. And so you can imagine these couple 100,000 Tesla batteries would be quite expensive. And so storing with batteries only might not be such a good idea. That is why there comes another thing into play, and I'm sure you have heard about it, and that is hydrogen. And hydrogen you can use to store electric power. You can make this hydrogen. Of course, you would make the hydrogen from electricity, not from natural gas. So you can pick up excess power in your grid, use the electrolyzer, make hydrogen, store it, and you can store it either. Your pipeline system alone would be a big storage area because you can pressurize it a little bit more or less, or you can have underground storage. There are many tests running now where they are checking out storage areas which are used for natural gas at the moment, whether they are applicable also for hydrogen storage, and that looks pretty promising. Now, if you have low solar and low wind power, you could electrify that hydrogen again. But there's one thing you can see by the size of these arrows here. A lot of power goes into the electrolyzer, and only a very small portion out of it comes out of the gas turbine, right? Because you have a lot of losses in the electrolyzer, and as well as in the gas turbines or fuel cells on that way. So it will be quite hard to make so much hydrogen, at least in Europe or in Germany, that we can only make it from excess power. We will pretty much have to depend on imported hydrogen also, because as you know, in Germany, we have sometimes nice summers, but we have long winters and not so much wind and sunshine reliably. There are areas in the world which are much better suited for that. And there we could have, for example, in North Africa, we could have a power generation there with also cheap land, reliable solar power or reliable wind power, and bring the hydrogen over to here. If we want to transport hydrogen, that is pretty much limited to pipeline transport, because there is also people who think about transporting hydrogen in ships. Therefore, it has to be liquefied, but that requires also a lot of power, and also the technology is not yet fully developed. So in my opinion, and in the opinion of many people, the hydrogen transport is pretty much limited mainly to pipeline transport. But now, if we have the hydrogen imported, the question is, what should we do with it? Should we all use it for making electricity with a large losses? The same reason why we're not using all natural gas to make electricity. We use the natural gas directly for heating our furnaces. Is then the same thought. If we have hydrogen available anyway, then why not use it directly with a much better efficiency than convert it to electricity and then you would heat our furnaces? And I will also, there are some other advantages of this I will explain later, is that if we use hydrogen for burning directly, we probably can still use our existing equipment and don't have to convert it to electricity systems, which is pretty difficult in many applications anyway. And so at least that's an option. Then we might also have to rely on other sources where the power generation can take place. For example, in areas with a lot of wind, like Chile, You know, at the Cape Horn there it's stormy all the time, and there we could have round the clock wind turbines running, making pretty cheap hydrogen, but there will be probably no pipeline running from South America to Europe at least. But there is another option which is discussed widely now, and then to transfer ammonia, hydrogen into ammonia, and ammonia has a property comparable to LPG. So under slight pressure, it can be liquefied, and then with a density which is comparable to propane butane, so LPG, can be transported in ships and then sent around the world in big tankers. What it is done anyway already today, because ammonia is a chemical which is used for fertilizer production, and it's a commonly shipped unit. Why ammonia and not making methanol or something else out of it? The reason for that is that ammonia is pretty much the only carbon-free fuel, which with these specifications. And carbon-free means you could use, for example, if you're sitting in Chile, you can use nitrogen, so basically air, water you have from the sea or from the mountains, and electricity, and make ammonia. While if you would make methanol or methane, you would have to have a carbon source and either ship the carbon in form of carbon dioxide or something else in ships there, which would be costly, or capture it from the air, but that is also quite expensive, and therefore at the moment ammonia is seen as a major carrier for energy in large quantities over large distances. It might be an exception for some other industries like the airlines. Airplanes will not be flown with ammonia likely, or hydrogen. There you might have the so-called e-fuels, fuels where you use carbon and hydrogen and mix it together to run in the existing airplanes. But like I said, in our industry, the heat treating industry, I think hydrogen ammonia will be the carcass. Ammonia now you can either crack and make hydrogen out of it, so separate the NH3 to nitrogen and hydrogen, and then have the hydrogen and use either the hydrogen direct in furnaces, or electrified in gas turbines or fuel cells to have that option. And again here, you can think of using the ammonia directly, thereby you save the cracker, you have a better efficiency. But burning ammonia is not so easy, and yet if you burn ammonia at the moment, which is hard to ignite anyway, but then if you are able to burn it, you are most likely to produce a lot of NOx, thousands of milligrams, or a very high NOx numbers you receive if you burn ammonia or ammonia containing fuel so far. So there's still something to do, which we have. But that's basically for us the three options you will have in the future. You will burn, after you burn natural gas, you can switch to hydrogen most likely, but of course in some cases it might also make sense to heat electrically, or in some cases, especially if you are not linked to a hydrogen pipeline, ammonia might also be an option. So our job at the moment is either electric, or we want to have fuel flexible burners which can use the fuel gas which is today in the grid. That's natural gas. Of course, at the moment there is no hydrogen, at the moment there is no green ammonia available, so it makes no sense to burn anything else than natural gas in these burners and furnaces. But to prepare for the future, we have to think about burners which are able to burn hydrogen, either natural gas or hydrogen, or mixtures between it. And we are also thinking about burners which are able to burn ammonia. Of course, you could think of also bio-LPG or biomethane, methanol, and something else. But the main things I think will be at the moment natural gas, fossil, or hydrogen, and in some cases ammonia. So is that possible? Can we use existing equipment and technology and further use it, or what is it? You take a first look at the fuel gas data from natural gas and hydrogen, you think, oh God, never possible. The calorific value 3 or 4 times higher for natural gas and hydrogen, the density 8 times higher, air requirement totally different. So in the first glimpse, it should look if you go from one fuel to another, you have to tear down everything and rebuild it. But you take a second look, it looks a little different. And I don't know whether everybody's familiar with the Wobbe index. The Wobbe index is a gas exchange factor used also by the gas supply industry to determine also in meters and pipelines what is the difference between 2 fuel gases. And it's a formula made out of a combination of the heating calorific value and the density to see through a given pipeline with given pressures how much energy is flowing through these pipelines or orifices or openings. And here you see natural gas and hydrogen are not so much apart from each other. That means if you send natural gas through a pipeline and with the same pressure you exchange the natural gas with hydrogen, you almost get the same 15% less, but at least almost the same amount of energy through the side pipelines. It means if you increase your pressure a little bit, you get the same through. And the second thing is for your air supply system, because you have a blower, you have air supply ducting and so on. Here, if you switch from natural gas to hydrogen, you use even less air. That means if you have an existing blower, it will be big enough, certainly, to supply also the air to your burner if you switch from natural gas to hydrogen. So from these factors, you will, through your piping and through your valves and orifice and everything, it looks good. You will get the air and fuel gas to your burner and through the burner. So that looks pretty promising. Now, of course, besides these Wobbe index and air requirements, there are some other things, characteristics, and that is the burning temperature, which is a little higher with natural gas, but only slightly higher. But a major difference between the 2 gases is the flame velocity. If you have a mixture of air and gas and you ignite it, it will be the flame will have a certain speed as it moves through that mixture. And that speed is quite a bit higher with natural gas. And here you see with a thermal camera 2 pictures of the same burner. It's a recuperative burner, a standard burner, C100 Recumat. If you have at the same power using natural gas and H2, what happens? Both will ignite fine, both will burst fine, but because of the higher burning velocity, your flame will move pretty much into the burner itself and will create higher temperatures in the burner. That means you can expect higher temperatures close to the burner, in the burner, and maybe also therefore higher wear and tear of the burner. So it might not last so long if you just take a burner, switch from natural gas to hydrogen and do nothing else. You might have damage on your burner if you are not looking into the things a little more closely. But other than that, it will probably work. One good thing about hydrogen, it is very, very likely to burn, so you will have no cold start problems. The burner will light pretty reliably all the time. So the only thing you have to take care that your burner lasts also. And that, of course, we and also other European burner manufacturers, I'm sure also in the United States, started, I think the main work started about 4 or 5 years ago to look into what do we need to change on the burners. And pretty much everybody now has solutions where you can say, here, at least we have a burner. You can exchange your old burner versus a new burner, or you can use your old burner and change some parts to make it work, or some burners might work without big changes, without major changes, where you can switch from from natural gas to hydrogen and be ready. So we did in 21 a first burner trial. Here, that is a horizontal annealing line for silicon steel, and with radiant tubes. And with radiant tubes, the nice thing is here you don't have to convert the whole furnace, because that burner, in that furnace you have a couple hundred radiant tubes installed, but you can test it on single burners to see, because it's a closed system, to see how the things work. And we converted here 2 burners from natural gas to hydrogen, let them run for a year, then take them out again and look at them. And really, there was not too much to tell about. The burners just performed. They survived. Nothing really. They didn't look different, any different than the other natural gas burners after a year, after 12 months of hydrogen. So in this, of course, we picked them because we thought that is a good demonstration area. But here now our customer is pretty much convinced if there will be hydrogen available, he can use the hydrogen and use this existing equipment. Of course, before you switch it, you would have to check for tightness and everything else, make a big maintenance checkup on all the burners. But if you have done that, he can be sure that he can run his furnace still with hydrogen. And that could be, for example, if there would be hydrogen available, and of course, if there would be a market for green steel. There might be customers which say, we don't want to buy steel which was heat treated by fossil fuels. So here, first test was quite promising for us. We have a second project together with ThyssenKrupp, the German steelmaker, the Aachen University, and our company, funded by the German Ministry for Economy and Climate Change or Climate Preservation, where we also want to use a radiant tube system, but here it's a vertical leaning line with double P radiant tube. And here the task was not only to switch from natural gas to hydrogen, but what can we do it to switch back and forth in a running production? That would be the case, for example, if they would decide to have a local electrolyzer on their premises next to the furnace, and if there's excess electricity, they could make hydrogen and then use hydrogen instead of natural gas. And if there's no sunshine or no wind, they would get back to natural gas. If there's enough sunshine or enough wind, they could go to hydrogen or a mixture of hydrogen and natural gas. And of course, we want to check if that can be done without manual interaction. So can it be done automatically without anybody having to go to every burner and readjust something just to make it happen on an automatic basis. And we set up a test rig, or actually the University of Aachen also set up a test rig with all kind of measurement devices or whatever, so they can also monitor everything, especially of course also the NOx emissions, because we don't want to switch to hydrogen and then have high NOx emissions. We want to be as low as we are today or even lower, and therefore we set up here a quite good test rig. Of course, we used the flux technology. That is a specific technology was developed by WS, our company. And since the flux or flameless oxidation runs without flames, that gives us the opportunity to get rid of that problem with the flame stability, with the high flame velocity of hydrogen. Because if there is no flame, there is no flame velocity. And we can have a burner which have very much the same characteristics running with hydrogen and natural gas with the same temperature distribution, because we avoid the flame anyway, also with the natural gas. We tested that. We tested also then the NOx emissions. And here we had 3 different configurations. We started with the existing configuration. That was a first setup with a red, you see the red curves. And here we started with pure natural gas on the left side, and then up to 100% hydrogen on the right side. And the left diagram is shown for flame mode at around 800 degrees or 840 degrees centigrade. And here you see we started in the red case with 200 milligrams per normal cubic meter, which is still below the German limit, which is about 350 in some cases and 500 in other cases. But if we go to 100% hydrogen, we are pretty much hitting that limit. So we are not really exceeding it, but we are hitting the limit with 100% hydrogen. Then we changed the configuration to the blue line with a different setup in the burner, and we could lower the emissions also with 100% hydrogen, but still more than natural gas. And then we had a third configuration where we still get it lower, still rising the NOx emissions when we go to 100% hydrogen, but then we switched the burner at 850 degrees centigrade to flux, and then you can see here a different characteristics. While with the first 2 configurations, we have low numbers, but still rising NOx emissions, whereas with the third configuration, we have really NOx emissions which are pretty much independent from the H2 content, and that's what we wanted to have. We want to say it doesn't matter if you run natural gas or hydrogen, we always have the same very low limits, and 100 milligrams per cubic meter, that is about 0.06 pound per million BTU. Here we are at maybe 0.04 or 0.03 pounds per million BTU, so that should meet even the toughest NOx regulations, and that is true for hydrogen and natural gas. With hydrogen, actually, you can have a correction factor because it relates on dry gas, and since hydrogen, you get more gas out, you can even have in reality a lower number. If you would relate it, for example, to pounds per million BTU, you would even see a decreasing number if you go to hydrogen. So that was very promising, but so far that happens in the lab. But in the next weeks, we will install it in the real line. So these are people from Thyssen and from the Elsa, our French engineer from the University of Aachen, and they will convert it, and then we will run it here for a year and see that the results are also holds true, not only in a lab furnace, but also in a real furnace, and we'll switch back and forth from natural gas to hydrogen and see what the burner is doing. The radiant tube is fully equipped with thermocouples so that we can also see is there an influence on the temperature uniformity of the tube and is there anything else to see. Besides that recuperative burner, we will also test regenerative burners. Regenerative burners have an even higher efficiency than the natural gas burners, and lately that's what we sold most of the time. United States, for example, some of you will know that there is a former Thyssen plant down in Mobile, Alabama. There are more than 700 of these regenerative burners installed in 4 galvanizing lines, and we tested these burners pretty much unchanged. Just like I said, a general maintenance checkup on the burners, but then we could use them with 100% hydrogen without further modification. And here we have efficiencies of more than 80%, and the NOx numbers are all the time below 100 milligrams. So very promising results here also for these burners. Of course, I can say that's not true for all the burners. If you have premix burners, some other burners, it might not be so easy to change, or it might be not possible at all to change. So if you have equipment you want to check if it's possible to fire hydrogen, please go back to your supplier of your heating equipment and ask. But one very important thing, if you buy new equipment, make sure, if you believe it or not, with the climate change and everything, but there might be in the future a market where customers want to buy green steel. That market might be 5, 10, 15, 20 years in the future, but you know, new furnaces, they last maybe 30, 40, 50 years. And so if you buy a burner today, please make sure that furnace and burner system is capable of running at least hydrogen. I think it's too early to say it should run also ammonia, because there are no burners available yet on the market which are flexible to use natural gas, hydrogen, and ammonia. We are working on it. And we are not the only ones working on it. Last spring, I attended a combustion meeting. It was more scientific, not so much practical, but here there were 100+ papers with the word hydrogen in their title. So a large amount of papers which dealt with hydrogen. Many institutes all over Europe are working on that problem, and more than 50 papers had the word ammonia in their title. So it's also a topic where many universities, very many research institutes are working at, and I'm very positive and hopeful that we will see results in the near future, that we are also able to burn ammonia with low NOx combustion, and I'm sure we will have it before the ammonia will be available on the market, because burning ammonia, green ammonia, that will be another 10 years, I would think, at least, before that hits the market, and these 10 years should be plenty enough to develop the system which are also able to burn ammonia clean, so that we will have all the options still using natural gas to a certain degree, but being able to switch to the other energy carriers like hydrogen, ammonia, if they're available. And if we know it works, we can lean back relaxed and for the future, because we know we have done our homework before things approach. So what would be my advice today, if we want to do something to reduce CO2 from our industrial furnaces, and maybe also to save money, because energy is expensive and is likely to become more expensive in the future. And here what you see, it's at least for Germany, but I think it's pretty much the same for the United States. You see the CO2 intensity of different heating systems. And since our electricity in Germany is to a large degree still produced in coal-fired power plants or gas-fired power plants, you have an electricity of about 500 grams per kilowatt hour electricity. If you burn natural gas, it would be 400 only, with an efficiency of 50%, so a cold air burner. But if you apply a hot air burner, for example a regen burner, it goes down to 250 about grams. That means today an efficient burner has half the CO2 intensity than an electric heating, resistance heating. So that means at the moment, if you switch from gas to electricity, you do no good to the environment, you increase your CO2 footprint. That might change in the future if the electricity production becomes more green and more regenerative. And I see it in about 10-15 years that we will have an equality of CO2 footprint, either of natural gas heating or electric heating. But there, of course, in 10-15 years, the green energy carriers of stored electricity, hydrogen, ammonia, will also kick in. And then you should have a good competition between these energy carriers, hydrogen, natural gas, electricity, and everybody has to figure out what is the best to use, what is the cheapest, the best solution to have, and to come, because competition, I think, is always a good thing to have now. But so if you install equipment today, it should be either, it should be first, efficient to save what you can save now, and second, it should be, and it is available on the market for most applications, it should be fuel flexible. So if your system, if hydrogen or ammonia will be, more likely hydrogen, will be available in the future, that you can switch to that hydrogen without building a new furnace or rebuilding all equipment. You will also see, if you switch to electricity today, you pay a high price regarding CO2, but also you pay a higher price because electricity is about 3 to 4 times or 3 times more expensive than natural gas. So over 10, 15 years, that would add up quite a bit. So I think the most economically, but also ecological solution would be efficiency first and then flexibility second. Yeah, that will bring me to an end. Thanks for listening. We believe in H2, we believe in green gas. By the way, on the picture here, on the photograph, that's not me, that's my father. My father drives a hydrogen car for 4 years now. I must say, I often borrow it from him if I have to go a larger distance. It runs flawlessly. You fill it up in 2 minutes. It runs noiseless, no problem so far at the moment. I think a very good solution. For local traffic, an electric car is fine. For long-range traffic, hydrogen cars are perfect. I think for the truck industry also. So hydrogen is a very nice fuel. It's clean burning, it's reliably starting, and it can be handled safely. I think not more dangerous than natural gas, and certainly safer than LPG because of the low density. If you have a problem, hydrogen goes up. And it's not accumulating on the ground. So I think with hydrogen, we have a solution available. Of course, the hydrogen must be available. It must be a competitive price compared to the other energy carriers. But if things go well, I think we have a solution here ready. The thing is now to do it. Therefore, we need politicians. We need to be prepared to pay the prices required for that, but then we can do it. Yeah, thank you for attention, and I would be glad to answer some questions.
Well, thank you so much, Dr. Wooning. That's a lot of really good, interesting information. I appreciate it. And as he said, if you have any questions, right now is a great time to enter them in that question box. But first, let me just ask a couple that came through here. One is, do you know when the hydrogen will be available?
Of course, I would have a, what you call it, I think, crystal ball. If I had it, it would be fine. No, of course, I don't know it. My guess would be, we have a lot of projects starting. My guess would be that we have first demonstration projects probably in 2 to 3 years, but very isolated and not economical, because in the beginning, the hydrogen will be expensive. But it depends a little bit. There might be a market coming up for green steel. For example, the area where our company is located, a couple miles from here away, is the headquarters of Porsche. You know, the nice cars they build, very expensive cars, and they decided to only use green steel in a couple of years, because they say if I sell a car for $100,000, it can well use some of that money to make green steel out of it. And so there will be a growing market for green steel where they're also willing to pay more for that steel if it's produced using no fossil fuels anymore. And that can create a market which develops faster than we think. So I think a general thing, a general availability that will take 10, 15 years at least, I would say. But in certain markets, I think it can go much faster than we would think.
Okay. Well, another question here. When you're switching existing natural gas pipelines to hydrogen, are you using existing pipelines, carbon steel pipelines, or changing pipelines and equipment with stainless steel?
No, there are a lot of tests we're running that you can convert natural gas pipelines to hydrogen, and they have to work a little bit on some gasket materials, compressor configurations, and so on. But in principle, many of the existing pipelines can be used, and also the piping on a furnace is usually you can use it also for hydrogen. You might have people heard of hydrogen embrittlement and things like that, but that's usually applying only at very high pressures and not for normal low pressures as we have them in the distribution systems for hydrogen. There, of course, we still not have yet all the standards available, and the legislation is not ready, but in principle, we can use it. We have in our industry, we have, for example, brazing furnaces and so on, which are using hydrogen as a protective gas anyway. So we have many industries in our we have many companies in our industry which are already using hydrogen not as an energy carrier but as a protective gas, and they're used to it. And it's not a really it's not a miracle to use it. It can be handled with the proper security measures and proper measures in place. It can be done. And like I said, the gas suppliers, they know they can convert certain pipelines from natural gas to hydrogen. It will be some work, but it can be done. By the way, up to 30 years ago, in former Eastern Germany, for example, in Berlin, we had all town gas, because they were not, it was basically an island, and they were not having any natural gas. They were using town gas, and that had 60% of hydrogen in there anyway, and they used that. So the switch from one gas to another took place here with the unification of Germany. And that was more difficult and more complicated than a possible switch from natural gas to hydrogen.
Okay. So what about the water production when burning hydrogen and its effect on products within the furnace?
Yeah, you have a higher water vapor contact. Some people think of the contact of hydrogen with the product, but I think that's not really an issue, because you burn the hydrogen before it hits the product. So your water vapor is increasing a little bit, but all the tests so far, which are so far we're running, did not show any influence. Your dew point in the exhaust will get a little higher with a higher hydrogen content. So especially if you're using very efficient burner, which can cool down the exhaust gas further, you might have condensation, and you have to look that condensate you can get rid of that condensate, not flowing back into the burner and setting everything underwater there. So there are some constructive measures which you have to consider, but in principle, all the tests so far, but there are still some ongoing tests show no influence on the fuel, on the heating characteristics, or on the materials.
Okay, thank you. Let's see here. Do I have to buy new burners to burn hydrogen?
In some cases, yes. In some cases, no. I have shown you with our flux burners, we are lucky. In most cases, I think we can convert them to hydrogen without major changes. Some changes might be necessary. Like I said, if you have a premix burner, for example, you might have, because of flashback, because of the flame velocity, you might have to buy new burners. So that is an issue. It's also in radiant tubes, for example, if you have very small diameters, it might be difficult to achieve low NOx numbers with an existing small diameter radiant tube. There you might have to switch to another system. But that you would have to contact your burner supplier to answer these questions.
Okay. And then, in your opinion, hydrogen or ammonia, which is better?
If you have hydrogen, hydrogen is better, because hydrogen is much cleaner, easier. It's not also ammonia is toxic. You have to. It smells awful. You have to take some precautions. So if you would be connected to a hydrogen pipeline, no questions, hydrogen would be would be the choice. But if you have, it's very difficult to transport hydrogen bottles. For example, for our lab, we have hydrogen bottles down there. It's 1,000 kilograms of bottles contain 10 kilograms of hydrogen. So it's not really an option to ship hydrogen in pressurized bottles around for energy purposes. There you have to be connected to a pipeline. So if you have hydrogen available from a pipeline, use hydrogen. If not, then check if ammonia is a good option, or in some cases also sorry, electrification might be the right option.
Mm-hmm.
For electrification, for example, electrification could be an option if your production can be very flexible. I think the electricity price in the future will fluctuate much more. It will not be a stable price of so many cents per kilowatt hour. It will be a price which goes from 0 to a very high level every day, up and down, depending on the supply and demand. And therefore, if you use a flexible system, electric system, where you can go up and down with your production and follow that price, so produce if the electricity is cheap and not produce if the electricity is expensive, it could be the case. For example, copper production or aluminum production, you can turn up and down these processes. If you have a continuous annealing line, you don't want to do that because you ruin your furnace and your product, but there might be different processes where it can be done.
Okay. Let's see, I think we have one more here. Do you have any issues to detecting flame while burning 100% hydrogen?
Yeah, that good question. Actually, the detection of flames with ionization works usually up to a hydrogen content up to 90%, but if you go to 100, so natural gas, 90% hydrogen. If you go to 100% hydrogen, ionization in most cases does not work. There you have to switch to UV cells, and there are UV cells which can detect hydrogen flames as well reliably. So that might have also might be a change you have to do in your system, but that's a reasonable change, I think.
Okay. Well, I think that about wraps up with the questions. If anyone would like to reach out to Dr. Wuning after this is over, he does have his email address up there, and you can certainly contact IHEA at any time if you have further inquiries. But I would like to thank everyone for attending the webinar, and especially Dr. Wuning. Thank you for putting this together for us. Remember to visit the IHEA website at www.ihea.org. We do have a sustainability tab where you can find more information and absolutely register for all the other webinars we have going through 2024. And if you have any questions, just let us know through the website. But please take a few minutes, watch for the link that will be sent to you, and give us your feedback on the webinars. We appreciate all of your comments and suggestions. And enjoy the rest of the day, everyone. Thank you.
Yeah, thank you for listening. Bye-bye.
Bye-bye.